Okay, so I will get that quiz graded back to you tomorrow so we can talk about it. Just a few housekeeping items before we go ahead and keep going. Don't forget that this Friday morning by 8:05, that is the deadline to retake your exam from last week. You don't have to have any of the related homework assignments turned in and completed. I would still encourage you to go ahead and look at those, come in for tutoring if need be, but you just have to come in and say you want to retake and you're good to go. I'm here after school, I'm here the next 2 mornings. Okay, so by 8:05. And also another reminder that this coming Monday evening, March 10th, over at Coronado High School, we've got our second of 4 AP prep sessions. This one's going to run from 5 to 7. So the first hour is going to be exponentials and logs. I believe Mrs. Wood is going to be covering those. And from 6 to 7, that's my section. So I'm going to be talking about graphing trig functions. That has actually been a long time since we talked about those. So if you are able to make it, that's probably going to be a good refresher. It's not mandatory. You know, we'd love for you to show up. If you have to show up late or if you have to leave early, that's fine too. Okay, we just love you to be there. Okay, that's all that I've got. Let's go ahead and take a look now at 2.5. Did anybody need a copy? Okay. I believe that's the last quiz we're going to have. I'm thinking about it. I can't promise anything because I haven't had the opportunity to sit down. If I do, I'll see if I can come up with something, but I just don't have anything right now. I can't do afternoon on Friday. Like during class? Yeah. Let me look at the roll and then I'll talk to you. Okay. Okay. Well, here we go. Thank you. Thank you. So we talked a couple of days ago about exponential functions, specifically what I said a little earlier today. If an exponential function has a vertical shift, then the y values won't change proportionally. At least they're not going to show that they should be changing proportionally. If there is no vertical shift, well then we'll see that proportional pattern that we've become accustomed to with exponentials. Now, after that, we went ahead and found a regression model for an exponential function. And then we finished up Monday by talking about how to do this by hand, to actually show the algebra to find the values of A and B. So now we are on the last part here, so we are almost done. Okay, so next up is the natural base E, or what we refer to as the natural number. So hopefully a lot of people are already familiar with E. We've used it a lot in mathematics. Okay, you got one right here. Why don't you pass that back, please?
Oh, I need mine too. I thought this was
the... Here you go. You need one too? Yeah. Okay. Oh, I'm going to talk about that in a second. Okay. So the natural number is roughly 2.718. The natural number E is often used as the base in exponential functions that model contextual scenarios. Well, what that means is we're just using it in real world applications and examples. That's what that's referring to. And it's in our first example today, number 4. It says the number of bacteria B in a particular culture can be modeled by the exponential function B of t equals 17 times e to the 0.31 t, where t is measured in hours. So they're giving me the function here. That's one less thing to worry about. Now, part A, let a of t equal a times b to the t be an equivalent expression for what we were provided. Find the value of b. So here's the thing. If these two are truly meant to be equivalent, well, that means I should be able to set this expression equal to this one. So that's what we're going to do. So a times b to the power t is going to equal 17 times e to the 0.31 t. Now, let's go ahead and start to compare these. For example, if they're truly meant to be equal, well, then what's a? A would not be e. A would be 17. They both have the same scalar factor. Okay. Now, because we're only trying to figure out b, we're only going to go ahead and focus on that portion of each function. So this is what we've got. We've got the sum base raised to the power t should equal base e to the power of 0.31 t. Now, because they have different powers, okay, I can't go ahead and say that B just equals E. Okay, think back to your exponent rules. This is one of those when you were solving exponential equations. Now, if I could go ahead and make both powers the same, say just to the t power, I would know exactly the value of B. So anybody think they know what we could do on this right side? And it's actually an exponent rule that we talked about very, very recently. The power rule, yes. What if I did this? B to the t equals, so right here, I rewrote it as E to the 0.31 in parentheses, and then raised that to the power t. Because remember, the rule is a power raised to a power. Well, that's going to be a product. You're going to multiply those. See, now that they have the same power t, I can go ahead and say that B should equal E to the 0.31. So B should equal E to the 0.31. And now we'll just go to the calculator and figure out what that is. Now, this is actually a really important skill to practice. That's where this comes in. This paper you picked up is 2.5, the assignment. So this isn't due until Monday. The key has already been posted, but you do have several opportunities to practice something like this on the assignment. So I would definitely take a look at that. But let's come on over here to the calculator. Now, the natural number is over here on the left side. It's 2 buttons to the left of 1. So I go ahead and click it. See, it already gives me base E. All I have to do is type in whatever power I want, in this case 0.31. So let's say the base is about 1.363. Okay. So my base is about 1.363. There we go. Any questions on what I did there? Okay. B, find the average rate of change of B of t over the interval from 1 to 7 hours. Okay, so we haven't talked really about this since Unit 1. So AROC, the average rate of change. Remember, what are we talking about here? What's a really simple, starts with S? Slope. The difference of the y's divided by the difference of the x's. But if you think back, remember, I did have you write that using the function notation. So I want to go from these values 1 to 7, and it doesn't matter. Let's go in this direction. So I'm going to go ahead and start out by saying b, because remember, that's what my function is called, b of 7 minus b of 1. So the difference of the y values, the function notation was your output y's, divided by the difference of the x's. So I'll just say 7 minus 1. Now, we also have the opportunity to remember something I showed you a little while ago. Let's store this function in the calculator so that it'll take care of that for me. I'll show you what I mean. So I'm going to come on over here. Okay, let's go ahead and type this in. So 17 times e to the 0.31. Now, I'm just going to go ahead and change it back to x because we're in the calculator. But remember, the variable itself doesn't have an impact on the problem. Now, I'm going to use my touchpad here to make sure that my cursor is no longer in the power. Does anybody remember how to store something? How do I get the arrow, though? I'm going to hit Control and then what? Okay, the variable button right here above the 9. You'll know you did it correctly because there's going to be an arrow. Now, they called this function b of t. I'm going to do the same with x. Now, I'm not going to go ahead and worry about capitalizing it. So I'm just going to say b of x. There we go. So now every time I type b in the calculator, it's going to refer back to this function. Like, let's say I want to know the number of bacteria 5 hours after we've started. Okay. Well, that would be about 80 bacteria. Okay. So because I've already got it stored in the calculator, well, why don't I go ahead and just type in exactly what we've got right here. So I'm going to come on back over here. So Control divide gives me a fraction. So I'm going to say b of 7 minus b of 1. Now, this is not going to show me the output values. And really, when it comes down to it, I don't need to know them. I just need to know the average rate of change. And then, of course, the 7 minus 1 is just 6. So this is my average rate of change. Okay, so what are we talking about in context of the problem? Well, it's increasing by roughly 21 bacteria per hour. Okay, this is what it's telling me over the 7 hours. hours. So I'm going to go ahead and approximate that, though. I'll say 20.952. So this is 20.952 bacteria. And I'll go ahead and abbreviate that. All right, well, let's go ahead and try C. Find the number of bacteria B predicted by the model after 15 hours. Okay, well, I've got my function. They're giving me the time t in hours, so all I have to do is plug that in. Now, this is still super easy because I've already got it stored in the calculator. So I'll just come on over here. I'm looking for the number of bacteria after 15 hours. Okay. So let's say 1,778. Because we're talking about the number of bacteria, I'm going to want to round that. Okay. So this is about 1,778 bacteria. Oh, and I just realized on this one, that should be bacteria per hour. I'm sorry. I can already hear the people who are watching this video like, you forgot the hour. Okay. Now, we're going through exponentials. How much of this is familiar to you from Algebra 2? Or at least aspects of it kind of coming through? You remember working with exponentials? I know the students I taught in Algebra 2 are going to say yes. All right. Okay. All right. Now, this wasn't originally part of the notes, but I'm thinking if we're going to cover exponentials, well, we need to start seeing problems like this. So let's add D to your notes. It says find the value of T when the number of bacteria in the particular culture is 1,000. So this time I know the number of bacteria, but I don't know what the amount of hours is going to be. All right, so we have to work backwards. So my equation would be to set the number of bacteria that I'm looking for equal to my function, 17 times e to the 0.31t. Okay. Now, how many people remember their log properties? Okay, now we haven't talked about logs in here yet, so I'm not going to worry. If you remember your logs, you'd be able to solve it super quick. So without that, we're going to have to use the calculator. Okay, so we're going to go ahead and put each side in the calculator separately, and then we're looking for the intersection. Now, because this is 1,000, that's a huge number. We can go ahead and make this a little easier on ourselves. Let's go ahead and divide through by 17. So this is actually the equation I'm going to work with. 1,000 divided by 17 is equal to e to the 0.31t. So I'm going to put in each of the sides, the left and the right side of the equation, and we're going to look for the intersection. So let's see what we got here. I'm going to do the exponential first. So we have e to the 0.31. Again, I'm just going to change t to x. Okay, so there's my growth curve. Now I'm going to hit tab. And I'm going to go ahead and type in the other one. Control, that's 1,000 over 17. Now the reason this one's going to be nice, I still don't see it immediately on my screen here, but 1,000 over 17, I'm trying to remember this off the top of my head. I want to say it's like 58.8, but it's definitely a lot quicker to get to instead of the 1,000. Okay. Now, when we do this, you folks know at this point, normally I like to go in and just change the window settings so that I can go ahead and get the screen that I'm looking for. But since we're a little pressed for time, I'm just going to go ahead and zoom out until I see it. Okay, so let's zoom out from the center. So I'm going to continue to zoom out until I see that intersection. Now I'm going to make sure to hit escape so that I don't accidentally zoom out again. So this is what I'm looking for. I'm going to go to menu, analyze graph. I said we're looking for the what? Intersection. Now remind me, what does it mean lower bound? There you go. If I'm looking for this intersection, lower bound means to put your vertical line to the left. I'm going to lock it in place with enter. So upper bound is the right. So there we go. It'll take about 13.1 hours for it to grow to 1,000 bacteria. Okay. All right. So let's see here. Oh, didn't let me do it. 13.1. Does that seem more familiar, the type of problem you may have done in Algebra 2? Okay, good, good, good. Okay. All right, we got one problem left, and it's not going to take us very long. Okay, Let me give myself a little bit of room here. So example 5, after 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by d of t equals a times b to the t, where t represents the number of years since the deer were first introduced to the area. The population of deer increases by 13% each year. Okay, well, if I want to write an exponential function in this form, okay, all we need are the two things. Now, a is going to be your starting point. That's your initial value. So that's super easy to find. How many deer are we starting with? 50. So I already know that a is equal to 50, right? Now, for b, when you're given a percentage, you're going to have to go ahead and either add or subtract that from 1. So this is usually for this type of problem, the type of function I use. Now, you may or may not recognize this. That's okay. A naught, that's your initial amount. So in this case, that would be your 50, right? Times, well, inside 1, that represents 100% of that initial population. Now, from that, we're going to add or subtract whatever my percentage is. Okay, and then, of course, we're going to raise it to your time t. Okay, does that look familiar? It's a super easy and quick way to write an exponential. So if I'm looking to find b, I'm going to take that 1. Remember, that represents 100% of what we're starting with. Am I going to add or subtract? Woo. We're going to what? We're going to add because we're increasing. Now, we'd have to change that 13% to a decimal, so that's 0.13. So my base has got to be 1.13. So here's my function. We're starting with the 50 deer times 1.13 to the power t. So the population is growing. It's not growing very quickly, but it's going to be growing. Okay. All right. Well, for part B, using this function, what's the population of deer after 6 years? Well, just like before, they're giving me the value of t. They just want me to go ahead and plug that in. Okay, so let's come on over here to the calculator. Let's document B out of this. So we started with 50 deer times 1.13 to the power of 6.
Please pardon this interruption. This is for students who are bus riders. If you ride bus 123 this afternoon, you will be riding bus 140. Again, bus 123 will be riding bus 140. If you ride bus 149, you will be riding bus 123. So 149 to 123. Students who ride bus 123 will ride bus 140. Thank you. Have a good afternoon.
Hey, you. Okay. So we're going to get about 104 deer. So we don't want to count them as a decimal because we're talking about whole numbers of deer. Okay. Well, C, or is everybody okay with that before I move on? Okay. Then C, it says find an equivalent expression for D of t when t is measured in months. Okay, so there's only going to be one part of this that's going to change. So I'm still going to have the 50 original deer. Okay, the base is still 1.13, but the power is no longer going to be t. And see, here's what you have to realize. You're only going to get that 13% gain annually, so at the end of a year. But we want the input now to just recognize months. Okay, any ideas on how we could do that? How many months are in a year? 12, so how will 12 affect the power? We're going to divide it by 12. See, because if I'm plugging in the number of months, so if I plug in 12, that's 1 year. 12 over 12 is 1. I get the full 13% gain. 24 over 12, that's 2 years, and it'll even go a portion of a year, so that's really nice. Okay. Now, for part D, this is the last problem. For part D, we're going back to the original function we found in A. It says find the time t when the population of deer is expected to reach 5,000. Okay, so because we're almost out of time, I'm going to go ahead and let you folks take a look at this one, on your own. But you should be setting 5,000 equal to 50 times 1.13 to the power of t. Okay, and you'll solve it in the calculator just like we did for D. Now, if you've done it correctly, here's what you should be getting: 37.68 years. I know what you're thinking. Oh dear, that is a long time to reach 5,000 deer. Oh dear. Okay, but there you go. That's all we got. And then tomorrow we'll talk about the quiz, and then we'll go ahead and start looking at 2.6. Okay, so let me go ahead and get this all shut down.